Welcome back. We're looking at putting everything together and trying to analyze the rational function that we're given right here algebraically so that we can sketch an accurate graph. So let's just remind ourselves a few things we need to take care of in the checklist. So I think looking at vertical asymptotes and holes first, that's kind of a good way to go. So let's go there. First thing I will do with my rational function that I have right here is I will factor it if possible. So let's look at f of x. And it looks like we have a trinomial of the special form in the numerator. So I believe that should factor nicely. Sometimes they do, sometimes they don't, but this one does. Factors of -5 that add up to -4. And it has a 1x squared, so I know there's an x in each of the binomial. So we have x minus 5 times x plus 1. And that is all over x minus 3. So at this point, I notice right away that we do not have common factors in the numerator and denominator. So right away, I could address in terms of there's holes or no holes. So I'll kind of write that just to remind myself. The other thing as far as finding a vertical asymptote, the function has not been reduced. It's impossible to reduce it. So if I'm going to look at finding the vertical asymptote, what I do is I'm going to set the denominator, which is x minus 3, equal to 0. And if I solve for x, by adding 3 to each side, the vertical asymptote is the vertical line x equals 3. So I'm going to make sure that we know that it's a line. So the moment I find an important characteristic about this rational function, I like to include it in the graph as I go. So as far as the vertical asymptote, if I'm looking at x equals positive 3, I'll do my best to denote that as a dashed line. And I could label it, it's not a bad idea, as well. So the next thing to address, if we're kind of looking at our checklist, look if we can find any horizontal asymptotes. So when we're looking for horizontal asymptotes, we're going to compare the degree of the numerator to the degree of the denominator. So if I look, I'll kind of label my work just to kind of show you. I'm looking at the degree of p of x. And when we refer to p of x, we're looking at the numerator. And it is equal to 2. And then we're going to compare this with the degree of q of x. And again, q of x is the denominator. And that's equal to 1. So in the comparison of what's happening here, when you compare the two degrees, numerator versus denominator, we notice that the degree of the numerator is higher. So just kind of restating it so you can see. Degree of p of x is greater than the degree of q of x. So what this tells us is actually there's no horizontal asymptote. So we definitely want to say no HA, or sometimes you can write none if that helps. So a lot of times when I know that there's no horizontal asymptote, the next natural question for me to look for is, let's look if we have a slant asymptote, or sometimes you say oblique asymptote. So I like to label it as SA, or you can say OA if you're talking about oblique. And kind of the clue I got from the trying to look for a horizontal asymptote, I noticed that the degree of p of x is 1 degree higher than the degree of q of x. And when that is the case, that means we do have a slant asymptote exists. And so how we're going to go about finding it is we're going to use division. So I like to look at my original function, and I will divide the numerator into, the denominator into the numerator. So I kind of notice when I'm looking at the division, the denominator is a binomial of the form x minus k. And that's good news because we can use synthetic division in this case. If not, you can use long division. It's either way. So I'll kind of set this up. What I'm looking to find when I use synthetic division, I'm going to list the coefficients of the numerator. That's 1, -4, and -5. And then I look at the denominator and I notice the k is going to equal to +3. A little bit of synthetic division review for us. And so if we use the synthetic division to figure this out, we're going to drop the 1 down, multiply the 1 by 3 to get 3. We add vertically, we're going to get a -1. -1 times 3 is -3. And we get a remainder of -8. Well, when we're dealing with slant asymptotes in college algebra, we really ignore the remainder. And we can look at rewriting our quotient. Notice that we divided, and if I can, I'll kind of give you an idea of what I just did. I'm just rewriting this over. I have x squared minus 4x minus 5 divided by x minus 3. So what I'm looking at is I notice that whenever I have x squared divided by x, it drops the degree down by 1. So therefore, when I look at my quotient, I should have 1x minus 1. Now what we do is we're looking for the equation of the line. And so technically, you don't really need to write the 1x if you don't want to, but the slant asymptote is that the equation y equals x minus 1. So remember, that's in the format y equals mx plus b, one of our favorite slope-intercept forms. And so that helps us graph the slant asymptote really quickly. We realize that the y-intercept b is at -1. So we can go back to our graph and begin at -1. And then use the slope to get to the next point on the line of the slant asymptote. So again, the slope is 1, or sometimes we say 1 over 1. So that gives us up 1 and right 1. So I go from my y-intercept, I count up 1 unit, right 1 unit, and I can keep going for more accuracy if I don't have a straight edge with myself. And so we'll use a dashed line to help us connect these points. And we can label it again, slant asymptote y equals x minus 1. So we've taken care of that. Very nice to see what's going to happen. So we kind of have dealt with dealing with and addressing the asymptotes, whether or not they exist. I want to look at the last few things. We're trying to say, let's kind of find some clear points on the graph if possible. So I would like to deal with finding the intercepts. So I'm going to go off to the side. A little more room, I guess, because I write a little large. But again, if I want to find the intercepts, what I'll be looking for is x-intercept and y-intercept. So if you remember, the x-intercept happens when y is equal to 0. So we're going to set y equal to 0. And what that means in terms of our function, if you look at it again, f of x was represented as y. So we don't really see a y, but we do know this. So what that means if we are dealing with trying to solve f of x, which is equal to 0, that is our x squared minus 4x minus 5 over x minus 3 is set equal to 0. Double check, I've got the signs right and the terms right. So now you're going to solve this resulting equation. Good thing we know about fractions. We have a single fraction equal to 0. So I'll kind of note that to you. And so anytime you have a single fraction, there's no sum of terms, no different fractions that are being added or subtracted. Every time you have a single fraction equal to 0, the only possibility that could happen when you're solving this equation must mean that the numerator is equal to 0. Okay, and so if you kind of think about it, just kind of a little thought bubble onto the side. In order for a fraction to be 0, it doesn't matter what's in the denominator, you have to have 0 in the numerator. I should be a little more specific. As long as we don't have 0 in the denominator. So 0 over 1, 0, 0 over 5 is 0. Again, 0 over even x minus 3 is 0, assuming that x is not equal to 3. So that leaves us with the equation x squared minus 4x minus 5 equals 0. And then we notice we've done this factorization already. It's a little quadratic equation. So we have x minus 5, x plus 1 equals 0. And that's going to leave us with x values. So this will be x minus 5 equals 0, or x plus 1 equals 0, or x equals 5, or x equals negative 1. So if you are being specific, if you're looking for this, what you'd want to say for yourself, the x-intercept, there's one of them at 5, 0, and the other one at negative 1, 0. So you definitely want to address this in terms of labeling it or writing it in the correct space or the line if they ask for them. But once I have this, what I can do for myself is go back and plot them. So again, 5, 0 and negative 1, 0. So 5, 0 would be about here, and negative 1, 0 would be about here. One last thing besides finding the x-intercept, I want to look at finding the y-intercept. And that's found by setting x equal to 0. And so what that means when you look at your original function, kind of scoot that over for you, we're looking at all the x's being 0, so you're actually plugging in 0. So that's f of 0. And what that means, you have 0 squared minus 4 times 0 minus 5 over 0 minus 3. And that's just showing work. A lot of you can do this a little bit more mentally if you want to. But we're left with negative 5 over negative 3, or we do a little reducing and we have 5/3. Now, if you're going to try to plot this, you can kind of name it 0, 5/3. But sometimes it helps so you see this in mixed number form. So you can use your calculator if you'd like, or you can go a little bit of old school and divide the denominator into the numerator. We get a remainder of 2. So we're really looking at 1 2/3. And that's kind of helpful for how we're plotting that. So it's a little bit of an estimation here. So I'll go back over to our graph. And if we're looking at the y-intercept and we say 1 2/3, you're kind of estimating about 2/3 of the way up. Then you have your graph. Now at this point, if this were a class where we didn't allow you to use a graphing calculator, you would then want to go in and find a lot of y values that correspond to x values on each sides of the asymptotes. So what I would have picked is I would maybe pick a few more x values along this x-axis to kind of get a general shape of the graph, as well as a little bit more x values along this side. And you can try stuff in the middle if you'd like, but then you'll kind of notice the pattern of some of these rational functions is that you probably won't see any values for x's in between these. Well, I guess you will. I shouldn't be so quick to judge. You'll see kind of more fractional values. It'll get closer and closer to the asymptotes, but they don't touch. So feel free. But because we have the use of our TI, and this is kind of why we paid the big bucks for this, we're going to use our TI to help us now with a little bit more of an accurate graph. So are you ready? Let's do it. Okay, so we're going to go into our TI. I'm going to switch over for you. And we're going to enter our rational function, press Y equals, there's the function editor. And what's really important with the rational functions is that you realize it's in fraction form. You want to make sure you're clear about this with the TI. So I'll start off by enclosing the numerator entirely in parentheses. And I'm using the original form of the function. Kind of saves me a little trouble with extra parentheses if I have to factor. So I have x squared minus 4x minus 5. So that's the entire numerator in parentheses. And we're going to divide by the denominator. Now enclose this in parentheses as well. So we have x minus 3. That's 3. And we'll press graph now. I think we're still in the standard viewing window. We will see. And you'll kind of have an idea now of how to draw the points of your function. So I'm hoping that you're kind of seeing like, oh yeah, the x-intercepts that we found and the y-intercept, it seems to agree. So this is the good news. The issue is that your TI doesn't give you the exact coordinates of the asymptotes. So this would be really important for you to understand so that you get a little bit more accuracy. So I'm going to copy this over just so that we can compare. And we'll go back to our work. Actually, we'll go back to our work. There we go. And I'll copy it onto the side just so that you can see that I want to do my best to kind of show what this looks like. So we can see right away, those intercepts pretty darn accurate. Even that y-intercept, even though it's in between the 1 and the 2. But the asymptotes aren't showing. But this is what we would do is we would take our graph and just kind of copy it as best as we can. And you can kind of now tell that the curve is going to hug the asymptotes. So just make sure you go through your points. And I kind of did that a little bit too often. I need to kind of hug my asymptote a little bit more. There we go. So check it out. It's a very nice way to graph a rational function. And we're so grateful that we have the TI because it saves us a lot of time. However, it's not impossible to graph. If you needed to, you can definitely pick a lot more x values and then you will get the pattern of the shape. So maybe if you'd like to be more precise or maybe your calculator batteries run out, then you can take it that way.